Hello friends, in this video I'd like to solve the following problem from the William Lowell Putnam Mathematical Competition 2015 problem B1, which is the first problem of the second day of this competition. Let f be a function thrice differentiable, 3 times in other words, having at least 5 distinct zeros. We wish to prove that f plus 6 times f prime plus 12 times f prime prime plus 8 times f prime prime prime, third derivative, has at least 2 distinct real zeros. So it's a pretty standard problem, but you have to know the method of showing such things. Here are my hints. First, you should define this function. G of x equals e to the power x over 2 times f of x. Notice that since our function since f has at least 5 zeros, g also has at least 5 zeros. Compute the third derivative of g and use Rolle's theorem in the end a bunch of times. So give this problem a try and I will see you in just a minute. Right, so as I suggested, let g of x be equal e to the power x over 2 times f of x for all real numbers x. Now, I will differentiate this function 3 times and I will get the following. You can verify it yourself that g prime of x can be written, I'm using product rule a bunch of times, it can be written as e to the power x over 2 f of x plus 2 times f prime of x. After second differentiation, we have e to the power x over 2 over 4, and this time we have f of x plus 4 times f prime of x plus 4 times f second derivative. Finally, after differentiating once again, it's x to the power e to the power x over 2 over 8, and we have f of x plus 6 times f prime of x plus 12 times f prime prime of x plus 8 times f third derivative. And we should do to get that this expression is exactly the same which appears in our problem statement. It's not a coincidence. Right, so now what I will do is to use Rolle's theorem, because notice that, or maybe let me enumerate at least 5 zeros of g. So for example, let alpha, beta, gamma, delta, epsilon be zeros of g. All right, and now let's put them on the number line. Alpha, beta, gamma, delta, epsilon. Notice that by Rolle's theorem, since our function g is differentiable, and it attains the same value at alpha and beta, it must have its derivative g prime must be 0 at some point in this interval. Let's call this a prime. Because of the same reasons, there is some number b prime in this second interval where our derivative of g is 0. Likewise, there will be a derivative, and somewhere here also another 0. By Rolle's theorem, there are alpha prime, beta prime, gamma prime, delta prime, which are zeros of g prime. Okay, So G prime has at least 4 distinct zeros. And you probably guess what will be happening right now. I will take my numbers once again, and I will find, again, by Rolle's theorem, zeros of function G prime prime. So in the interval from alpha prime to beta prime, since our function G prime attains the same value at the ends, there will be some number alpha double prime, beta double prime, and for example here, gamma double prime. So again, by Rolle's theorem, there are alpha prime, alpha double prime, beta double prime, gamma double prime, such that, or which are zeros of G double prime. And again, let's iterate our reasoning once again. If I take a third derivative of G, somewhere in the interval from alpha double prime to beta double prime, somewhere there will be number alpha triple prime, and somewhere between beta double prime and gamma double prime, somewhere there will be beta triple prime, which will be the zeros of our third derivative. So let's write it once again. By Rolle's theorem, there are alpha triple prime less than beta triple prime, which are zeros of G triple prime. Which means that, notice, let's go back to our function G triple prime of x, third derivative of G. Notice that this part right here is never zero. It's never zero. So this means that this function underlined in yellow must have zeros at alpha triple prime and beta triple prime. This means that f plus 6f prime plus 12f double prime plus 8f triple prime has two distinct real zeros. Of course, they're real distinct zeros. Alpha triple prime and beta triple prime. And this is exactly what we wanted to prove. This closes our proof. Very nice problem, I'd say. So remember this problem. If coefficients standing to our derivatives of our function are just right, then this trick with multiplying by some exponential function works. The only tricky part is to guess what should be in the exponent. In this case, x over 2 was good. In other cases, some other exponent may be good, but remember this general method. And that closes our problem. So thank you very much for watching, and I will see you next time. Goodbye.